And it would be very convenient for us to express everything as a function of heat flux, which is the heat exchange rate per unit area. Because as we already learned the heat transfer mechanisms, we know how to calculate those heat flux. But so for Q in, if we express everything, use Q double prime, which is heat flux, should be the Qx, the heat flux in x direction, times the cross-section area. For conduction, consider the conduction inside the volume, the surface area perpendicular to heat flow. In x direction should only be dy times dz. It's the cross-section area, not the total surface area. And simply for heat flux in y direction, what is the cross-section area for conduction heat flux in y direction? In y direction, the surface perpendicular to y, what's that?
1.
dx times dz, right? And the last one is a heat flux term in y direction, in z direction, times the surface cross-section area perpendicular in z direction, which is dx dy. And simply for outflow here, if we expand everything as the heat flux term, which but we need to consider they are occur at a different location. In each direction should plus its dimension from the original. Nothing difficult here. But how can we know? There is a common trick I think you guys may heard from the first year of the class. How can we know to consider the modification to capture the temperature variations over the dx, dy, dz? How can we to further compute those heat flux as a function of its original term? The common trick here is use Taylor series expansion. We would in x direction. This is the heat flux in x direction at x plus dx. We can express it, use its component at its origin plus its variation over x direction. And what am I missing here? It's variations over x direction times how the distance, its dimension, dx. I use approximate here because we neglect higher orders in the Taylor series expression. We only consider the first terms there. So we can express to capture the variation in distance and expand this term using the component at the origin x, variations in x direction times how much it varies. That's the distance of dx. And very similarly, it can be applied in y direction and the z direction too. We expand this as using the component as from its origin and use only the first term of its Taylor series expansion. Then if we substitute what we have here into the heat flow out, let's calculate the net heat flow rate together. Compute Q in minus Q out. So substitute everything we listed there. Is a heat flux term in each direction times the cross-sectional area minus the heat flows out. Let's start with the x direction first. Note that everything has a double prime here, which means it's a flux term. In order to calculate the rate term, we still need to times the cross-sectional area because given by the product of heat flux times the corresponding cross-section area. So for heat flows out, this term should be also a minus or minus plus here. It's more variations here. And times the cross-section area perpendicular to x direction. And y direction. Cross-sectional is dx, area is dx dz. And similarly in xz direction. Can we see the material, the items we can cancel with each other? With which one? The first term of heat flow out in x direction. Anything else?
The second and the third as well.
How about the heat flow in y direction? Can be cancelled with heat flow out in y direction, the first term. And simply, we have only 3 items left here. Everyone finished here? I will left our beautiful element control volume there. But I only calculate the net heat flow rate first. We will substitute everything in your note with generation, with heat stored in together. So after cancel the material terms they have, our net heat flow rate is simply given by what does this term? What's the meaning of this term? The product of the dimension is 3. The volume, right? But so it should be dx. That's what we end up after expanding the heat flows out using the first term of Taylor series expansion. Then remember, I already erased here, but it should be in your guys' class notes. The generation term is the volumetric term times the volume, and the heat stored term with the assumptions closed system, which means mass is constant, and no phase change, which means specific heat is constant. We have the heat stored per unit time here. What we have done so far is just to start from our universal heat rate balance and then define our control volume. But this time we define infinitesimal control volume with the dimension of dx, dy, dz in 3 directions. Then nothing new here. I identify the Q in, Q out, Q generation, heat stored. The final step is combine everything together. Into the heat rate balance. Q in minus Q out, we already have, say minus. And the volume of the element cube plus Q generation, volumetric heat generated term times the volume of our element cubic. And finally, the heat stored, density specific heat, heating or cooling rate times its volume. Can we also cancel something here? As we can see, the volume appears in each term on both sides of the equation. Cancel it. Then we end up with is that the same as the previous mentioned heat diffusion equation? We end up with some the final energy balance end up with equation here that it looks the exact same as the diffusion equation here. The generation term is the same, and we see some heat the heating or cooling rate, but not the Laplacian operator, right? They are not exactly the same. How can we deal with those heat flux term with their variation in each dimensions? If we consider only the heat transfers happened inside the control volume, the only heat mechanism we should consider is conduction. Because contact, convection, radiation, they are surface conditions. But if we only consider heat flows inside that control volume, we should only consider conduction. What the equation should we use or apply to compute conduction? Heat flux. So we need to apply Fourier's law in each dimension. What's the expression for x direction? Minus something times conductivity something. Right. Should be the minus times thermal conductivity times the temperature derivative, the gradient in x direction, and similarly in y. And in z direction. If we would like to write as simple as those 3 equations there, we need an assumption. Isotropic, because we assume the thermal conductivity term is uniform in all 3 directions. Otherwise, we cannot express them as this because K, the thermal conductivity, sometimes can vary in directions. But if we assume now the control volume is isotropic, which means thermal conductivity is the same in X, in Y, in Z, which will make our derivation much simpler. And substitute what we have, the heat flux term in 3 dimensions here, into our derived the modified energy rate balance. We will have. Now consider the term in x direction. So we substitute minus k. And similarly in y direction. substitute its conduction heat flux here. And then Z direction. The volumetric generation and the heat stored will remain. And the minus sign, which means positive. Minus y, minus k, minus here. So that's what we have. And to make the derivation even simpler, let's assume k is constant here, which means it does not vary with the positions and does not change with the time. It keeps constant for any point inside the control volume and for any time we consider. If k is constant, then it can be taken out of the derivative. And just for, out of convenience, we use the combination of the three sector derivatives. We use the square of a downward triangle and call it a Laplacian operator. It is when we first introduced Fourier's law. The Laplacian operator is two single downward triangle, but with a dot product. The sum of the unmixed sector derivative. You cannot have dt over dx and dy, but unmixed second derivatives. Then these complex three terms can be simply expressed use the Laplacian operator only. Volumetric generation and heat store. And if we divide the density times specific heat on both sides of the equation, at the same time, the equation still holds. Then we define some material properties termed as thermal diffusivity. The symbol is alpha. And it's defined as the ratio of thermal conductivity over the density of the material and the specific heat. It has a unit of square meter per second. It represents how effectively the material respond to the thermal conditions, the change of thermal conditions. We would have heating rate or cooling rate. K over rho Cp here is simply alpha. Alpha times temperature, the curvature of temperature profile, and plus the ratio volumetric heat generation over density over specific heat. That's our heat diffusion equation. That's exactly what we have here. So start from our universal energy rate balance with our defined element control volume. Then we identify each term: generation, heat stored, net heat flow, Q in minus Q out. We can land at this heat diffusion equation, which gives us the temperature distribution how it varies with time, how it changes with as a function. If we see here, it's a function of positions x, y, z, as well as time. With this single equation here, we can, if we solve with some prescribed boundary conditions, we can know the temperature value of every point within the medium at any time. We are not go deeper with how it's super complex to solve this partial derivative equation with 4 independent variables, x, y, z, t. But what matters in our class is we need to have a basic understanding of which terms inside this equation. And we have a common sense that start from the simplest energy rate balance. We can calculate the temperature distribution and the evolution with temperature just with our QE minus Q out plus Q generation equals Q heat stored.